So the last problem 3, there was nap sort. So problem 3, nap sort. This one was a trick. This one is a funny one. So the setup for this problem is we were trying to sort an array. We want to sort an array of n up to 2 times 10 to the 5 integers. But of course, this is not just a typical sorting problem. There's some weird sorting mechanism to do this. The way it is that there are two groups. There's Bessie, and there are all of Bessie's helpers. And so what happens is Bessie, she will initially pick a pile of integers. She will pick some integers from the array, and she will sort them themselves. So if Bessie picks k integers, then the first one, then the way that her sorting algorithm works, that she's going to take the minimum element each time and push it into the back of a new list. So the first one, she's going to take a k time to fix the first one. She's going to take k minus 1 time to fix the second one. She's going to take k minus 2 times to fix the third element, and so on and so forth, right? So in total, she's going to take k times k plus 1 over 2 time to sort like her portion of the array. Okay, and what about the helpers? So the helpers are going to have some leftover elements like A1, A2, up to like A of n minus k, because the helper is going to have n minus k elements. And what the helpers are going to do is they're going to take each element and literally have them sleep by like their value. So this is going to sleep for A1 seconds, it's going to sleep for A2 seconds, and sleep for n minus k seconds. And then once they're done sleeping, they push this array to the end of the list. They just push it to the end of the list. They push to the end of the list after A1 seconds. They push to the end of the list after A2 seconds. They push to the end of the list after A minus k seconds. And so now we want to know, well, first off, we need to make sure this is sorting it properly, because there are some cases where the helpers might push their elements too early. Like they push it before Bessie would push her elements, and then the array is no longer sorted. So we need to make sure this is actually properly sorted. But the second thing is so now we are oh, and also like in case of a tie, if like two things happen at the same time, like Bessie tries to push an element from her sequence, and one of the helpers tries to push like a sleeping element, then Bessie takes priority. And we want to know what is the minimum possible time to sort the array under these conditions. And the sorting is like the minimum possible time is like we get to choose like which how many elements Bessie takes, which ones she chooses, etc. And we want the minimum possible time to sort it. Okay, so how can we approach this problem? Well, at a high level, let's suppose that the maximum among all the helpers. Let's consider the maximum among all the helpers of like their A elements. So this is going to be an upper bound of how long it takes, right? Because the maximum value needs to wait for that amount of time. But then also, Bessie's part takes k times k plus 1 choose 2 time to sort. So the answer, basically, if the array is properly sorted, then the amount of time it will take is the maximum of like all the array elements the helpers took, and the how much time it took for Bessie to sort her portion. And this kind of motivates fixing the maximum among the helpers. So let's say we sort all the AI. I'm going to draw some array elements here. Let's suppose we sort some all the AI, and now let's suppose that the first one that sleeps, or from the back, the last one that sleeps is this element. So that means that Bessie is going to take all of these into her array. So this is the maximum AI that we have enumerated. Then we basically want to find, among this portion, we want to find the minimum amount of elements that Bessie can take. Let's say the minimum B, such that Bessie takes B from this prefix and the array is correctly sorted. Okay, so this is actually kind of interesting now. So essentially, we have the subproblem of like, well, first of all, let's consider loosening our conditions. Does there even exist a valid B such that Bessie can take B elements from the prefix and then the whole thing is properly sorted? Does that B even exist? And it turns out that you can always prove that it exists. So let's consider the following subproblem. I'm going to give you a subproblem. Let's say we fix K, like how many elements that Bessie takes, and we have n elements where n is greater than or equal to K. Then if we fix K, this basically partitions the array to like K plus 1 intervals, where let's say these elements are strictly less than K, these elements are greater than or equal to K, but they're less than K plus K minus 1, which is equal to 2K minus 1. So basically the time it takes before the second elements from Bessie is put into the array. Let's say these elements are all greater than or equal to 2K minus 1, but less than 3 times K minus 3. So like K plus K minus 1 plus K minus 2. Let's say this interval is here. So let's say there are no elements that are greater than or equal to 3K minus 3 and less than 4K minus 6. And then finally, these elements are going to be greater than or equal to 4K minus 6, right? So in this case, K was equal to 4, and we had 5 intervals partitioning based on whether they must come before or after each of the K elements that Bessie will be putting into the array. Then the question is it possible for Bessie to pick 4 elements so that the remaining elements are correctly partitioned? So one way that works is that Bessie picks this element. One way that works is that Bessie picks this element, this element, this element, and this element. Because now everything to the left of 1 is less than K. Everything in between 1 and 2 is greater than or equal to K, less than 2K minus 1. Everything in between 2 and 3 is greater than or equal to 2K minus 1, but less than 3K minus 3. Nothing in between here, and everything greater than 4, nothing exists either. Okay, so I mean, this kind of passes the eye test. We want to prove that in general this is always possible, and so the proof goes something like this. We have these intervals. Let's instead consider the slots in between the intervals. We're going to draw kind of these kind of like pairs of slots. So we'll redraw this diagram. And what we want to do is basically want to match. We basically want to match array elements to slots so that the remaining elements are partitioned correctly. Partitioned correctly meaning that the stuff that are not picked, the stuff that was not picked are on the correct side of the slots they should be in. So like an example of a wrong partition was if we did something like this. This is wrong because this element was supposed to be to the left of the second slot, but it's actually to the right because it's to the right of the second element we pick. And so now we will just do the following algorithm. We're going to start from the prefix and we're going to consider the first point. Yeah, we're just going to start from the beginning. Yeah, and we're going to consider the first point, the first position where let's see. Yeah, so we consider the first position where there are more array elements than at least as many array elements as slots. And then we're just gonna go ahead and assign them. And then we kind of have the this recurring, or actually, let's do it this way. So we're gonna consider the first position where there are an equal number of array elements and slots. And that if that doesn't exist, if that doesn't exist, then we just kind of assign them like this and it works out. Right? But suppose that doesn't, or this like, so we just assign it like this and it would work out. But let me give a better example. Let me give a test case where it's not so trivial to just like figure out how to assign the things. So you have like 3 slots here, and then 1 slot here, 1 slot here, 2 slots here. The only condition is that the number of slots should not exceed the number of total array elements. Okay, let's do this. So for here, let's consider the first prefix where we have at least as many array elements as slots. And then we will assign all the array elements to the slots, and then consider this like recursive subproblem. So this is going to be a proof by induction. As long as the number of array elements remains greater than or equal to the number of slots, This is our we can just apply the induction hypothesis and like go down to like a smaller case. So here we have three slots and we have at least three array elements. So we assign all of them and we move to this top problem. Now we have this is the first prefix where there are as many slots as array elements. So we just assign it here. And now we're in this situation. Now the first prefix, so this is true, is here. So we just assign it here. And then finally we have this. We assign it here. And indeed, all the array elements are partitioned correctly in this particular example. So the only ones that were not taken were these ones, and they are to the right of the final slot. And so we can always apply an out. We can always apply that out. So we can prove now that like it doesn't matter as long as there are n elements and Bessie is taking k less than equals to n elements. There's always some valid like set of k elements she can pick so that the array is properly sorted. Okay, so why is that relevant? Let's go back to what we were originally trying to do, which is originally we were trying to fix. We had a bunch of array elements in a row, and we were fixing that the maximum elements that is not taken by Bessie. So this is this is sleep. This is the maximum element that sleeps. And then Bessie takes these elements. And now for here, because we know that as long as k is less than or equal to 5, it is always possible to pick elements to properly partition this. So all we have to worry about is if this element is properly partitioned. So we just need the maximum or the minimum k such that let's say this is k1 or k2 elements on this side. The minimum k1 element such that it should be k1 plus k1 minus, or wait, such that the sum of k1 plus k2 plus k1 plus k2 minus 1 plus dot 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 plus up to k2 plus 1. So basically, the amount of time it takes to sort for Bessie to process all these elements in the front is less than this array element. Let's call this A. This needs to be less than A, so that the this skip element is pushed back far enough. And then A needs to be less than equal to this same sum. So k1 plus k2 plus k1 plus k2 minus 1 plus up to k2 plus 1 plus k2. And if this is satisfied, if this inequality is satisfied, then by our proof earlier, we're going to be able to pick valid elements to fix the rest of this stuff. We delay this array element sufficiently far back, and then these elements are all picked by Bessie. No issue there. And so therefore, this is a valid sorting condition. And so once we find the minimum k for which this is true, then our answer for this particular for this particular choice would be the maximum of A and k1 plus k2, that same formula, right? K1 plus k2 times k plus 1 times k1 plus k2 divided by 2. And then we just try this over all possible k2. So over all possible choices of the maximum, we try this. So in total, there are n different maximums that we can fix. And for this, doing all of this, you can either directly solve for it, you can either directly solve for this, because it should be like some sort of quadratic, or you can just do binary search if you don't want to work out the details. The binary search works in, I say, log of n as well. So this is an O of n log n solution. Yeah, so let's just quickly summarize what we did. Basically, we are fixing the maximum elements that is given to a helper that sleeps. The Bessie takes all the elements prior, and then we just need to figure out the minimum number of elements Bessie needs to take from here, the prefix, so that this entire thing is sorted validly. And it turns out all we need to do is check this inequality, because we don't need to worry about picking the wrong elements that this prefix part is not sorted properly. We just proved that it's always possible to pick prefix elements to sort the prefix properly. So we just need to check this inequality, and the code ends up being relatively short. And it's O of n log n. Okay, now so we have a lengthy explanation, but are there any questions? Okay, let's return to the slides then. Give me 1 second. Let me open the slides again. Okay, so we are almost out of time, but yeah. Yeah, hopefully everyone can see the slides. So yeah, basically, these are kind of the knowledge points I would say you roughly need to solve these problems. Of course, like it's not just binary search, not just greedy, but certainly having good foundations in those topics would be are necessary to be able to solve approach these problems. And so we have listed the relevant XPM courses that correspond to each of these topics. And yeah, we also have the XCamp USACO report card that you can get if you want to register for that. So you just visit the website and claim your USACO report. And yeah, are there any questions? I know we're almost out of time, but I can quickly answer if there are any remaining questions. So apologies for technical difficulties today, but we got to the end eventually. Yeah, okay. I guess there are no questions. Is the session's over?
Yes,
Yes, have
Dorian, maybe you can ask questions because
mm.
it's pretty good time to discuss with our coach and teachers.
It's okay if you don't have questions now. Yeah, I think I'll see you like 2 days from now. Okay. All right. Yeah. Thanks for coming, everyone. Yeah.
Yeah, thanks. Thanks for joining our live solution. See you next month.